Edexcel Core Pure, second order differential equations 1, homogeneous case. Auxiliary equation with complex roots. So this is our second order linear equation with constant coefficients, and we're still looking at the homogeneous case where the right hand side is 0, and the auxiliary equation is am squared plus bm plus equals 0. That's the form that it would have. Now, if the discriminant is negative, we may end up in a situation where m is alpha plus or minus beta I. So we've got a real part which is alpha and the imaginary part which is beta. In which case we'd have to set out our general solution like this. Y equals a e to the first root x plus b e to the second root complex root x. If we use our laws of indices now to rewrite this as a e to the alpha x times e to the beta x I, and likewise here b times e to the alpha x times e to the minus beta xi. Now we can pull out a common factor of e to the alpha x, a e to the beta xi plus b e to the minus beta xi. And we've seen in a previous video that this bracket can be written in the form p cos beta x plus q sine beta x. So the real part of this complex number alpha appears here, and the imaginary part beta appears here. We still have the two constants p and q in our general solution. So if the discriminant is negative, we could get an imaginary pair of roots, or as in this case we could get two complex roots. And the important part of this is to realise that the alpha would appear there and the beta would appear there and there. When you're doing this in a homework situation, you wouldn't have to put those two lines of working in. You could go straight from the auxiliary equation to your general solution. So in this example, we could be trying y equals a e to the mx, and that would produce the auxiliary equation m squared plus 2m plus 17 is 0. I'm going to solve this by completing the square. M plus 1 squared plus 16 is 0. Therefore, m plus 1 is plus or minus 4i, and therefore m is minus 1 plus or minus 4i. Of course, you could solve the quadratic by using a quadratic formula as well. So now I can see my two complex roots for m because the discriminant of the auxiliary was negative. And now I can go straight to my general solution. So first I deal with the real minus 1 part, so that's y equals e to the minus 1x, and then I deal with the 4i part by having p cos 4x plus q sine 4x. Notice there's no I in the general solution, but it does contain two arbitrary constants p and q. So the auxiliary equation could be solved with a formula or by completing the square, but the important thing is to recognise the complex roots for m. The real part, minus 1, is the coefficient of the x there, and the 4 is the coefficient of the x in each of the trig ratios. And we can have a look at this general solution in more detail using a GeoGebra file. So at the moment I've set p equal to 1 and q equal to 0, so our solution is y equals e to the minus x times cos 4x, and you can see that particularly if you look at x is 0 that this is trying to behave like a cos 4x. When x is 0 we can see that we are getting that amplitude is 1. The interesting thing here is as x gets bigger, then e to the minus x decays. So you can see these blue dashed lines showing you the e to the minus x as it decays towards 0, and when x is negative then e to the minus x would get exponentially bigger and bigger. So that's the solution when p is 1 and q is 0. If I change p, I can change the look of the solution. I'm trying to make the amplitude bigger, but of course the amplitude is decaying as well. And if I go back to p is 0, if I make q 1 and p 0, we can see that it goes through the origin. It's trying to behave like a sine wave, but again it's got this exponential decay, and as I change q I can change the look of this decaying sine wave. If I start changing p and q, I can start to change the look of the curve. Notice it's not necessarily symmetrical in the y-axis, all goes through the origin. We can change what's called the phase shift, we can make it move around, and you'll be looking at some of these characteristics in your core modules. It's also worth noting that the y-intercept will always be the value of p. When I start changing q, I do not change the y-intercept, so the y-intercept here is p equals 3. Some other things to notice: it's clearly oscillating. The period of each full oscillation is 2 pi by 4, and for those of you interested, this is a good example of what's called damped simple harmonic motion, and this is a type of simple harmonic motion that you may come across soon. And that brings us to the end of second order differential equations 1, the homogeneous case.